400 million miles from Earth, a spacecraft moving at 130,000 miles an hour dropped toward the most violent storm in the solar system, and for a few seconds, everything the mission had spent years preparing for came down to a single number so small it barely qualifies as a number at all, 1/100th of a millimeter per second ekand. That is how fast Juno's velocity changed as it passed over Jupiter's Great Red Spot in July of 2019. It sounds like nothing. It is, in fact, one of the most consequential measurements ever taken of another planet, because that impossibly tiny shift finally answered a question that had haunted astronomers for nearly 2 centuries. How deep does the storm go? And when scientists took that same signal and turned it into sound, they produced something no human being had ever heard before: the literal voice of a storm's gravity, recorded from almost 500 million miles away. To understand why this moment mattered so much, you have to go back further than Juno, further than NASA, further than modern astronomy itself, to a spring evening in 1664, when an English scientist named Robert Hooke pointed a telescope at Jupiter and noticed something strange: a dark oval sitting in the planet's southern half. Hooke didn't know what he was looking at. Telescopes were still primitive, barely capable of resolving detail on a planet hundreds of millions of miles away, and there was a real possibility that what he saw was nothing more than the shadow of one of Jupiter's moons crossing its face. A year later, an Italian astronomer named Giovanni Cassini looked again, and this time there was no ambiguity. Cassini tracked the same oval feature returning to the same position over and over, night after night, and used its motion to calculate something remarkable. Jupiter's rotation period, just under 10 hours, one of the fastest spins of any planet in the solar system. Cassini called it the permanent spot, and for the better part of 50 years, astronomers watched it, recorded it, and assumed they were looking at a fixture of Jupiter as stable and enduring as the planet itself. Then, in 1713, it vanished from the records. No dramatic final sighting, no explanation, just silence. For over 100 years, nobody reported seeing anything like it again, and when a new dark oval reappeared in the historical record around 1830, and was documented in far more detail after a particularly striking apparition in 1879, astronomers simply assumed it was the same storm, waking back up after a long, quiet century. It wasn't until incredibly recent research, analyzing centuries of historical sketches, measurements, and rotation data, that scientists began to suspect something unsettling. The math didn't add up. The size, the drift rate, the behavior of Cassini's permanent spot didn't match the storm we call the Great Red Spot today closely enough to be the same object. The current Great Red Spot, the one Juno flew over in 2019, most likely isn't a 400-year-old storm at all. It's probably a completely different storm, one that began sometime in the early 1800 seconds, meaning the object every schoolchild has been told is a 3.5-century-old landmark might actually be less than 200 years old, a storm still, in cosmic terms, uncomfortably young, and still very much active. Whichever version of the story is true, one thing has never been in dispute. Whatever is spinning in that region of Jupiter's southern hemisphere is enormous, almost beyond comprehension. At its widest recorded extent in the late 1800 seconds, the Great Red Spot measured wide enough that you could have placed 3 entire Earths side by side across its diameter and still had room to spare. Even today, after more than a century of documented shrinking, it remains wide enough to swallow our entire planet whole, with room left over. Wind speeds along its outer edges regularly exceed 400 miles an hour, more than triple the wind speed of the strongest hurricane ever recorded on Earth. And unlike a hurricane, which draws its energy from warm ocean water and dies the moment it crosses onto land, the Great Red Spot has no ocean to feed it and no land to kill it. Jupiter has no solid surface at all, just endless layers of gas growing thicker and hotter the deeper you go, which means there is nothing in the storm's environment that would naturally force it to weaken, break apart, or dissipate the way every storm on Earth eventually does. It is a high-pressure anticyclone, spinning counterclockwise in a way that's actually the opposite of how most hurricanes rotate in the southern hemisphere, and it has apparently been doing this uninterrupted for at minimum 190 years, possibly much longer. For all that time, one basic architectural fact about the storm remained completely unknown. Was the Great Red Spot a thin veneer of color and wind sitting on top of Jupiter's atmosphere, a kind of cosmetic feature with no real substance behind it? Or did it reach down into the planet like the root system of a tree, anchored into something far more massive and permanent than a surface weather pattern should ever be? This wasn't a minor curiosity. The answer would tell scientists whether Jupiter's visible weather, the bands, the storms, the swirling colors we can photograph with an ordinary telescope, are connected to the planet's deep interior, or whether they're an isolated skin floating disconnected on top of something scientists still don't fully understand. And there was no obvious way to find out. You cannot dig into a gas giant. You cannot send a submarine into clouds made of ammonia and hydrogen. Every previous spacecraft to visit Jupiter, from Pioneer to Voyager to Galileo, had photographed the storm beautifully, but had no way to measure what was happening beneath it. That is the mystery Juno was quietly built to help solve, even though nobody on the original mission proposal had the Great Red Spot's depth specifically in mind. Juno launched from Cape Canaveral on the 5th of August 2011, riding an Atlas V rocket into a 5-year, 1.7 billion mile journey across the solar system, looping past Mars and swinging back by Earth in October of 2013 to steal a gravitational boost that would fling it the rest of the way to Jupiter. It arrived on the 4th of July, 2016, and executed one of the most nerve-wracking maneuvers in the history of planetary exploration, a 35-minute engine burn that had to fire at exactly the right moment, with zero margin for error, to slow the spacecraft enough for Jupiter's gravity to capture it into orbit. Too early, and Juno would miss the planet entirely, sailing off into deep space with no fuel left for a second attempt. Mission Control held its breath and watched the burn complete perfectly. Juno was in orbit. From there, Juno began threading itself through one of the most hostile environments any spacecraft has ever willingly entered. Jupiter is wrapped in radiation belts so powerful they could fry ordinary electronics within hours, generated by the planet's magnetic field, which is roughly 20,000 times stronger than Earth's. To survive, Juno's most sensitive electronics were sealed inside a titanium vault, essentially an armored chamber built to shield the spacecraft's brain from a radiation environment intense enough to be lethal to a human being almost instantly. Juno was designed to dive close to Jupiter's cloud tops on a long looping polar orbit, swing in from one pole, race past the planet at extraordinary speed, and then arc back out to a safe distance before radiation exposure could accumulate to dangerous levels, repeating this high-speed pass again and again over years of operation, each orbit taking roughly 53 days to complete. It carries 9 scientific instruments built to map the planet's magnetic field, measure water and ammonia hidden deep in its atmosphere, search for a solid core, and photograph the planet's swirling storms in a level of detail no previous mission had achieved. Nowhere on that original list of goals was anything about measuring a storm's depth using gravity. That idea came later, and it came almost by accident. A scientist named Marcia Peresi, working at NASA's Jet Propulsion Laboratory, realized that one of Juno's existing instruments, its gravity science system, built primarily to help map Jupiter's overall internal structure, could theoretically be repurposed for something nobody had tried before. If the Great Red Spot had significant mass concentrated beneath its visible clouds, that mass would exert its own small gravitational pull on anything passing directly overhead, including a spacecraft. And if Juno could be sent low enough and close enough and precisely enough, that pull might leave a fingerprint, a tiny, measurable change in the spacecraft's velocity as it crossed directly above the storm. It was an elegant idea, but an enormously risky one. Nobody knew if the signal would even be strong enough to detect against the overwhelming gravitational noise of the rest of the planet. And executing the flyby meant sending an irreplaceable, multi-billion-dollar spacecraft skimming low and fast directly over the most violent storm in the solar system, with essentially no room for correction if anything went even slightly wrong. In July of 2019, Juno made 2 such passes directly over the Great Red Spot, hurtling above the storm at roughly 130,000 miles an hour, at an altitude low enough that engineers described the encounter as an acceptable risk rather than a safe one. As it crossed overhead, Juno kept transmitting a continuous radio signal back toward Earth, a signal so precisely tuned that any change in the spacecraft's speed, even one too small to ever be felt by a human being, would alter its frequency in a measurable way. On the ground, a massive dish belonging to NASA's Deep Space Network locked onto that signal from over 400 million miles away and listened. This is the same basic principle behind the sound an ambulance siren makes as it speeds toward you and then away, rising in pitch as it approaches and dropping as it recedes, a phenomenon called the Doppler shift. Juno's radio signal would do the exact same thing, just on a scale so microscopic that detecting it required treating the spacecraft's entire trajectory almost like a stethoscope pressed against the side of a planet. If the Great Red Spot were nothing more than a thin, shallow smear of colored gas, there would be nothing underneath it dense enough to register. The signal would pass through clean, undisturbed. But that isn't what happened. As Juno crossed directly above the storm, its velocity shifted by a genuinely staggering degree of precision, as small as 1/100th of a millimeter per second, and the Deep Space Network caught it. That number is almost impossible to make intuitive. It is a change in speed roughly comparable to detecting the width of a human hair's worth of velocity difference, sensed from a distance spanning almost the entire diameter of the inner solar system. And it was consistent. It happened both times Juno crossed the storm. Something down there had mass, real mass, concentrated densely enough to physically tug on a spacecraft, traveling at more than 100,000 miles an hour. When scientists modeled exactly what kind of mass distribution could produce a signal shaped precisely like the one Juno recorded, the answer settled the 200-year-old debate. The Great Red Spot was not a surface feature. It extended down at least 300 kilometers beneath the visible cloud tops, roughly 186 miles, with the full range of the data allowing for a maximum depth of around 500 kilometers, or about 310 miles. To put that number into perspective, 500 kilometers is deeper than the boundary most scientists use to define the edge of space above Earth's surface. If you flip that measurement downward instead of upward, the Great Red Spot reaches further into Jupiter than the edge of space reaches away from our own planet. The storm was rooted, not floating. It had a foundation, and that discovery connected to something else Juno had already been quietly mapping for years, an entirely separate and even more staggering structure hidden inside Jupiter, its zonal jets. These are the deep, powerful currents of wind that circle the entire planet at different depths and different bands of latitude, the underlying engine that drives the visible bands of color you can see through an amateur telescope. Juno's earlier gravity measurements, going back to 2018, had already revealed that these jets extend down thousands of kilometers into Jupiter's interior, reaching depths where atmospheric pressure climbs to roughly 100,000 times what we experience at sea level on Earth. Compared to that, the Great Red Spot, sitting at a maximum of 500 kilometers, is actually shallow. It's a passenger riding on top of a much deeper, much more powerful current system rather than the deepest structure in that region of the planet. But being shallower than the jets doesn't make the discovery any less significant. It proves for the first time with hard data that Jupiter's visible storms and its hidden interior currents are not separate systems operating independently of each other. They are connected. What we can photograph on the surface is the visible expression of something enormous happening far below, in a part of the planet no camera will ever be able to see directly. This is the moment where the sound enters the story and where it becomes something more than a curiosity. Juno's gravity data wasn't originally captured with the intention of producing anything audible. It existed purely as a Doppler-shifted radio signal, a scientific measurement meant to be analyzed as numbers on a graph. But when engineers took that same signal, the one generated by Juno's velocity, bending under the storm's gravitational pull, and shifted its frequency down into the range of human hearing, something extraordinary happened. The result wasn't static or noise. It was a slow, uneven, breathing rhythm, rising and falling in a pattern that mirrored the exact moment the spacecraft's speed bent under the mass of the storm below it. You are not listening to Jupiter's wind. You are not listening to thunder or clouds or any conventional sound at all, because gas giants like Jupiter don't actually have the kind of atmosphere that produces sound the way Earth's does. What you are listening to is something stranger and in its own way more profound. It is the literal gravitational signature of a storm wider than our entire planet, converted directly into audible frequency, a recording of pure mass, felt across 400 million miles of empty space, and translated into something a human ear can process. It wasn't the only strange sound Juno had captured. Years earlier, in June of 2016, as Juno first crossed the boundary of Jupiter's colossal magnetic field on its way into orbit, its WAVES instrument recorded the encounter with what's known as the bow shock, the point where the supersonic solar wind slams into and is slowed by Jupiter's magnetosphere, roughly analogous to a sonic boom here on Earth. That recording, when converted to sound, produced a low grinding hiss, the sound of Jupiter's magnetic shield physically deflecting the constant stream of charged particles pouring out from the sun. Then, in June of 2021, during a flyby of Jupiter's largest moon Ganymede, Juno's WAVES instrument picked up the electric and magnetic radio emissions produced within the moon's own magnetosphere. And when scientists shifted those frequencies into audible range, the resulting 50-second clip sounded almost unnervingly alien, a series of high chirps and whistles that mission scientists themselves compared to something out of a science fiction film. Juno's principal investigators described listening to it as feeling like riding along with the spacecraft on a journey no human being will ever physically take. Taken together, these recordings form something unprecedented in the history of space exploration, an entire audio catalogue of a gas giant system that no human ear could ever otherwise access, built not from microphones, because there is no air in space to carry sound, but from radio waves and gravitational fingerprints, painstakingly translated into something we can actually process and feel. None of this happened by accident, and none of it happened easily. Juno's extended mission has continued well past its original endpoint, and by the time of its most productive years, the spacecraft had executed millions of individual commands, completed dozens of orbits, and returned more than 3 terabits of scientific data, all while flying through one of the most radioactive environments in the solar system, protected by little more than a titanium vault and careful trajectory planning. Along the way, it has resolved other long-standing mysteries too. It discovered that Jupiter's core is not the small, dense, sharply defined ball scientists once expected, but something far stranger, a diffuse, partially dissolved core that appears to blend gradually into the surrounding layers of hydrogen and helium, suggesting Jupiter's formation was far more violent and chaotic than the clean textbook models had assumed, quite possibly the result of a massive early collision that churned the planet's insides before it had the chance to fully settle. It found bizarre storms clustered in perfect geometric patterns around Jupiter's poles, cyclones the size of countries arranged almost like the petals of a flower, holding stable formations that shouldn't, by any conventional model of fluid dynamics, remain as orderly as they do. It even discovered evidence of what scientists nicknamed ammonia mushballs, slushy hailstones formed deep in Jupiter's atmosphere that may help explain why the planet's ammonia levels looked so puzzling and inconsistent in earlier measurements. Every one of these discoveries added another piece to the same underlying picture Juno was quietly building, a picture of Jupiter as a planet whose visible face and hidden interior are locked together far more intimately than anyone expected before this mission began. And yet, for all of that, there remains something quietly unsettling sitting underneath the entire Great Red Spot story, a fact that gives all of this discovery a strange and pressing urgency. The storm is dying, not suddenly, not dramatically, but steadily, and it has been for well over a century. In the late 1800 seconds, astronomers recorded the Great Red Spot at its largest documented size, wide enough to fit 3 Earths across its diameter. By the middle of the 20th century, that width had noticeably contracted. Measurements taken in recent decades put it at barely wide enough to fit a single Earth, a loss of roughly 2/3 of its recorded size in under 200 years. Nobody knows with any real certainty what happens next. It's possible the shrinking will eventually stabilize, settling the storm into some smaller, more compact, but still enduring form. It's possible it will continue contracting until it simply can no longer sustain itself as a coherent structure and dissolves entirely the way smaller, shorter-lived red spots have been observed forming and then disappearing elsewhere on Jupiter within just a few years. Some researchers have even suggested the storm could eventually fragment, tearing into smaller pieces the way a slowly weakening vortex sometimes does before it finally breaks apart, which means the storm Juno flew over in July of 2019, the one whose gravitational pull was strong enough to physically bend a spacecraft's velocity and produce a sound humanity had never captured before, may already be measurably smaller, weaker, or structurally different than it was on the exact day that recording was made. It's entirely possible that Juno's flyby captured something close to a final full-strength reading of one of the oldest continuously active structures in the solar system, taken not long before it began a more serious, irreversible decline. If that's true, then this isn't simply a scientific curiosity from a few years ago. It's closer to a recording of a living thing's voice, taken shortly before that voice began to fade, the kind of data future scientists may look back on as an irreplaceable snapshot of something that no longer exists in quite the same form. There is also a wider lesson tucked inside all of this, one that extends far beyond Jupiter itself. The Great Red Spot isn't the only giant storm ever observed on a gas planet, and it isn't even the only one to raise this exact mystery about depth and permanence. In 1989, NASA's Voyager 2 spacecraft photographed a similarly enormous dark storm on Neptune, nicknamed the Great Dark Spot, a vortex roughly the size of Earth itself, spinning in Neptune's atmosphere with wind speeds, among the fastest ever recorded anywhere in the solar system. Just 5 years later, when the Hubble Space Telescope turned its attention back Neptune, the Great Dark Spot was simply gone, vanished entirely, only for an entirely new dark storm to appear elsewhere on the planet not long after. Neptune's storms, it turns out, may come and go far more quickly than Jupiter's, and scientists still don't fully understand why one giant planet's storm system can persist for centuries, while another giant planet's equivalent storms seem to appear and dissolve within just a few years. Every answer Juno provides about the internal structure of Jupiter's storms adds another data point toward understanding that broader mystery, not just for our own solar system, but potentially for the thousands of storm swept gas giant exoplanets astronomers have identified orbiting other stars, worlds we will likely never send a spacecraft to directly, but whose internal weather we may eventually learn to understand by extension through exactly the kind of techniques Juno pioneered above the clouds of Jupiter. Juno is still out there right now as you're watching this, still completing its long looping orbit roughly every 53 days, still diving close to the cloud tops and swinging back out before the radiation becomes too much to survive, still listening. Every flyby is another opportunity to catch some new signal bending in a way scientists don't yet understand, another chance to translate the invisible tug of gravity or the crackle of a magnetic field into something we can finally process and hear. Nobody expected when this mission was first designed that one of its most memorable discoveries would come not from a photograph, but from a sound, an accidental byproduct of measuring how a storm's mass bent a spacecraft's path through space. And that raises a question worth sitting with long after this video ends. If the gravity of a storm can be converted into something we can hear, and that sound can tell us not just what a storm weighs, but how deep it reaches, and how close it may be to fading away entirely, then what else is out there right now, completely silent to our eyes, simply waiting for the right instrument and the right idea to finally let us listen? If stories like this pull you in the way they pull me in, go ahead and subscribe to the channel, because this is exactly the territory we spend our time exploring here. Leave a comment and tell me what struck you the most. The fact that this storm might not even be the same one Cassini discovered in 1665, the staggering precision of a measurement smaller than a millimeter, or the strange idea that gravity itself can be turned into sound. I'd also love to know where in the world you're watching this from. It's always fascinating to see how far these stories travel, and if you're not ready to stop exploring yet, there's another documentary waiting for you right here on the channel. So stay a little longer, and let's keep digging into what's really out there, hiding in plain sight above our heads.